Hello, yeah, welcome back to chapter number 2 in ADS. And I'm going to pick up from where I left. So I'm going to make a new namespace, new workspace, and I will call this as chapter 2 in ADS. Okay, so I'll call this chapter 2 in ADS. As far as the libraries are concerned, I'm going to use a nonlinear demo kit, right? So this is available with the tool, and people would be much better of using this rather than using what I recommend here, right? So let's go ahead and do that, and also set up technology immediately after creating the library. So that will be your resolution. So you'll say create workspace, and this says use this layout technology, say finish. Okay, so you have a blank workspace here. So let's look at some things which we left last time we didn't show you. So let's just go through some slides before we proceed. Okay, so here I'm going to look at simulation and data visualization, which we have done earlier, but let's just have a look at what that is. Okay, so performing simulations, you can use the menu item simulate and then hit simulate, or you can use simulation setup to set up some of the things with simulation, right? So what it lets you set up is the file. Okay, so it says use the cell name for the data display window and also for the data set, right? So it says use cell name for the data set, right? So the data set is going to be the same as the cell name. Okay, so in that case we can choose to it to be a different name. So you can say a name which is different from the cell name. So you can write it over here, right? So this is the name which I have given, and the data set is targeted towards a data display window, which is the same name as the design itself, right? And then you can hit simulate. Okay, other ways to start simulation is going to be, you can either click that button which I showed you, or you can use a menu item and say simulate, or you can use one of these buttons, right? Okay, so the data display, so as soon as the simulation finishes, the data display window opens automatically. So it has a menu bar which kind of looks like this, and here the most important which I use is marker, right? So marker to place the marker. Other than that, you can have multiple pages in a data display window. So you can open a new page in the same data display window. uh, okay, so then the toolbar has the same functionality as the schematic window. So all this like view all, view the selected portion, zoom in, zoom out, and stuff like that. And then you have the save, new folder, and stuff like that, right? Or a new data display window. So this is same functionality as a schematic window. Then here you see the data set, right? So the data set, the data display window requires at least one default data set. So the first one it's going to pick up. So for example, if we named it as LPF ideal, it will pick up that, right? So you can put a default data set. This is like, you can zoom into the graph. So basically you can use zoom in and zoom out into the graph, not the display window, the graph, right? And then you can view all inside the graph. So basically you can zoom out all the way to whatever the extents of simulation are, right? So you can zoom in and out inside the graph. Then here there are markers here, right? So you have a peak marker, a valley marker, right? So stuff like that, a simple marker. And then here if you are more than one trace, then you have a special marker over here. Okay, so these are peak and valley markers. These are maxima and minima markers. This one is a multi-trace marker. This is allowed on a rectangular plot only, and then it gives you a haphazard result if you do a multiple plots or a stack plot. Then you can, a display window can have pages, right? So you can adjust your display into different pages. And then again on the left hand side there is a palette which has got a rectangular plot, a Smith chart, a table. You can write equations. You can end the current command. So it's the same as in schematic, or you press escape, and then you have polar plot here. Then there's a stacked rectangular plot, right? There is an antenna pattern, there's a polar plot. Then you can put shape or a text. So that's that. And this is the area in the graph or in the display window where you put all the graphs. So the way to do is the same way as the components. It's not that you drag and drop from the button. You click once on the button, and the command basically is going to highlight a change in the cursor. The cursor can become a capacitor, inductor, or something like, a dotted, ghost character, which will stick to your mouse, right? And then you can click anywhere in the schematic, in case of schematic window, or display area in the data display window to place it. Okay, so we'll be able to do that. Okay, so we can put a rectangular plot, and as soon as we put a plot, there is a window which opens, and then on the left hand side you can choose add, and then you can choose what is the format of the data to be displayed, like in dB or dBm, magnitude, phase, real part, imaginary part, or a time domain signal, and then click OK, and that will become a rectangular plot. This we have already done the exercise, right? Okay, so now let's look at another exercise. Okay, I want to see if by mistake I leave, I do mistakes in my circuit. Like for example, the topology was like this, and I had this connection which was taken off, or this ground was taken off, right? So let's say they were gone. So then what is it going to do? So you go to tools and you do a check design. So when you do that, you can look at the details. Okay, so it'll tell you where are the open connections and stuff like that. So there are two warnings, and it'll say, for example, here the L1 pin was not connected, so that L1 pin was not connected, or it can refer to the ground not being connected, right? Okay, here you can change the options. So you can look for open, you can look for bus connectivity, okay, nodal mismatches, schematic versus layout. You can look at parameter value mismatch, schematic versus layout, and then you can say overlaid components that has pins connected. So what usually used to happen is, instead of placing one component, you by mistake place two components, one on top of the other. So unless you move them apart, you will not be able to know that. But this will tell you that you have two overlaid components, right? So that warnings would be issued. Okay, so after this you can go to tools and you can get more information about a component, right? Okay, so it will show you the selected items and what that is, the netlist information. So that's all about that. Then we have already seen, okay, simulation starts with a netlist, and in netlist for component values you can insert variables. So what's the advantage? So if you just do the simulation, what's going to happen is it's going to netlist and then run the algorithm on the netlist, give you the results. Now in case of tuning, you will be able to change the variables in the netlist without re-netlisting. So basically when you do a simulation, every time you hit simulate button, it's going to re-netlist the entire circuit. Now if the circuits become large and you have to change one component, why would you netlist it again? So that's what a tuning does, right? Okay, so tuning means that you netlist once, but then you have variables which you can change. So that's a tuning fork which is a button for for tuning. You can choose the component, and then you can choose the component variable. For example, inductor has two of them, L and R. So here the two will appear, but for capacitor there's only one here which is highlighted. You can choose that and hit OK. So that will show up in the tuning parameters window as a slider. Okay, so the neat feature here is if you have a tuning window open here and you move the slider, you can see the real-time change in the plots, which we have already seen. So the effect of the change you can see, right? You can store in between values with a name. You can reset to the start values or revert back, or you can update the component values to the current value and update the schematic, right? So we are done with the tuning part, and we have also seen the optimization part. Now let's go and explore the simulators, right? So let's look at DC simulation. So we will use the demo kit and its transistor for doing the DC simulations. Okay, so you can add them later on by using manage libraries, right? So you can start at the start, you can add a library or number of libraries, or in case you want to add it later, you can go to file. In the main window you can go to file, manage libraries, and then you'll be able to browse to the lib.def file of another library and attach it. So you can go to add the design kit from favorites. So you can basically just choose the one of the listed, or you can go to add user favorite library PDK, right? Okay, so we are going to make a new schematic and we'll call this as DC characteristics, and we will have a palette for the demo kit with the include file, right? So this is a palette for the demo kit PDK, and there is an include file here. So ER equal to 12.9 is telling me, and H equal to 100 micron is just telling me that this is a 4 mil substrate. It's a 4 mil wafer. Thickness of the wafer after thinning is 4 mil, and the height of the gallium arsenide is 100 microns or 4 mil, and the epsilon is 12.9. So that's what it is telling you. So we create a circuit like this. Okay, so here what's coming from the demo kit? What's coming from the demo kit is the transistor, right? And the include file in these capacitors. So transistor, which is going to be FAT1 model, right? And then capacitor. Now why there are two capacitors? Because there is a limit on the maximum size of a capacitor here. Okay, so it's telling where all these components are coming from. So it's coming from tech include, the include, and this is FAT1. This is your capacitor, and this is that, and then these are coming from frequency domain sources. So this is VDC. So we are setting two biases. One is the drain to source, other is the gate to source. So it's a depletion mode FAT, so that's why there is a negative VGS, and then there is a supply. Okay, so that's that, right? So there they are coming from, and these are the lump components. So this is the ideal choke or DC feed. So basically that's that, right? So you know where these are coming from. So when you are new to ADS, you should know where these components are placed. Some are in the PDK palette, some are in the sources frequency domain, some are in the lump components, right? So we'll create a circuit like this, and then if you want to measure currents, you have a probe component which is coming from probe components palette, right? iProbe. Then you can name it as IDS, for example. and these are the terminations, right? So these terminations are coming from S parameter simulation palette. So this is term 1 and this is term 2, right? And then the wires are coming from here, or there is a variable here. So VGS and VDS are variables, so I need to add variables. So that var is coming from that variables. Okay, so we have set up the circuit. So every circuit requires a simulation controller to be placed on top or at the top's most schematic level, right? Simulation controller can be found in every simulation palette. So let's say I want to do DC simulation. The first button is going to be the DC controller. And then if you want to do a sweep, I have already talked about the nested sweeps. So there is a parameter sweep for every simulation. So this is DC controller. Okay, so if you double click on that controller, you would be able to set what you want to sweep. So for example, if I want to sweep VDS, so that's going to be from, let's say, 0 to 10 volts, steps of 0.1 volts. So there are 101 points, right? So this we have already talked. Then we will do a linear sweep. We have already talked about it, right? Okay, once the simulation would be complete, the data display window will open. Okay, and then you will be able to plot the probe current. So that's how it is done for different VGS. So parameter sweep is specified in the parameter sweep component, right? This we have already seen earlier. You can also use add versus. So you can put IDS versus VGS rather than VDS, right? So it will look like this, add versus. And that's how trace expression looks like. So that would be transfer characteristics. Okay, so let's just follow this exercise and let's do the simulation. So let me put this aside. Okay, so first thing I'm going to do is I'm going to make a new schematic. So earlier, I told you it's better to organize things into folders. So I will call this as DC characteristics folder, and in this folder I'm going to create a new schematic, and I will call this as DC CHAR. Right, and say create schematic. Okay, so a schematic window opens. Okay, so I have the demo kit, nonlinear demo kit palette available here. So first thing I'm going to do is I'm going to place a FAT1, right? And here I will just refer to the model. So let's see in simulation what model do I have. What's the size of the transistor? So I'm just going to repeat the same stuff. Okay, it's the 4 fingers, 100 micron each, and there is one device, model 11. That's what it is. 4 fingers, 100 micrometer each finger, model 11. Right, and there are two terminals given for the source. So let me do F5 to move the text to the side. Okay, one more thing is I'll talk about stabilization later on. So for now, I'm just going to directly connect it. So that's connected. Then I am going to add in some components like coupling caps from the demo kit itself, right? So I'm going to use the largest value. So I guess if I double click this, and I can put the capacitance value to be 2.0 5. Let's see if it allows you. No, it doesn't. It says that this is going to be too large. 2.3. So it allows me 2.3. Okay, so that's a square which is this cross this. So you cannot edit this in this PTK. You can only change the component values. Let's say if I want a bigger capacitor, what would I do? I would just copy this, right? So there's a copy button over here. I'll just copy this over here, and then if I press F5, I can move the text here like this. So this is going to be now 4.6 picofarad because they are in parallel. That's connected. And same thing I will do on the input side. I'll just copy this. So there's a copy button over here. So I'll just hold this somewhere, copy it over here. Okay, so that's connected, right? And then I want two chokes. So basically RFC, ideal choke, or DC feed. So if I go to LUM components, I will find these ideal components which are called DC feed. Now this is a ghost which is attached to my cursor. Now if I place it, I can rotate it while I am holding it. So like this, I can hold this, and now I can change it to wire and connect it. So just wanted to tell you, I also want to see what's the current drawn, right? I can place it here also. So I will go to components, probe components. So basically here I have a current probe. Now the thing to notice is the arrow is going from left to right in the ghost figure. You can see here the left to right measurement, while I'm expecting the current will flow from right to left. So I'm going to mirror this along y-axis. So now it is in the appropriate direction, right? So it will give you a positive current, and I will name this as IDS. So this will give me the current values. We'll connect them like this, and then I have got LUM components. From the sources frequency domain, I have got VDC. So I have got one, and I have got second one. Okay, so here I can just add the ground pins and give them a name. So I can call this as VDS, and I can call this as VGS. Correct? And then I can just connect them. Now, like in C language, if you want to use a variable, you have to declare its type. Same thing you have to do over here. You have to declare a variable. So I just place the variable component. I'll just double click this. So once you double click it, you can put here VGS, and these are case sensitive. So whatever you put here, same thing you have to type here, and it has a default value. You say apply. Now VGS, then I can do a VDS. So I can change this name to VDS, right? And the VDS, I can give a default value of, let's say, 4, and instead of apply, I say add, because if I say apply, it will replace it. If I say add, it will add it. And I can edit this to be minus 1 volts. Okay, that's okay. Say apply. So okay, so now I have declared two variables. One goes to the drain supply, other goes to the gate supply. So we are done with this. Then the next thing which we need is a termination. So I'm going to go to simulation as parameter, and here I have terminal 1 and terminal 2, right? So I can just place them, give them the DC ground, connect them to the circuit like this. Now this circuit is ready for simulation because it has the right terminations here. You have VDS, you have VGS, you have grounds, and then you have the input terminal, output terminal, which are terminated into 50 ohms. So this circuit is can be simulated now. What else do we need? These models are coming from a technology include file. So if you go here, there's a tech include file here. Okay, so you have to place that here. So what are the options here? I have thermal on. So what this means is enable thermal analysis of FET. So that's what it is, as it says. And then I also need a simulation controller. So I want to do DC simulation, for example. So I'll go to simulation DC, and here is my controller. Now in the controller I can sweep one of the voltages here. Okay, so let's say I want to sweep the inner loop as VDS, and I want to see from 0 to 10, right, in steps of 0.1 volts, right? So they are 101 points. Okay, the next thing is I want to sweep the gate voltage, right? So I have to do a parameter sweep now. So that's parameter sweep would be over here, and here I will sweep VGS. So be careful about the case sensitivity. Whatever you entered here, that would be over here. And here I'm going to sweep VGS from minus 3 volts to 0 volts in steps of, let's say, 0.5. So yeah, so there are 7 points, and say okay. Now these two for loops are independent. So here, if you want to display what you are sweeping, you can go to display, sweep variable, start, stop, step, say okay. So basically you are sweeping this VDS from 0 to 10 in steps of 0.1, and then the other one is sweeping VGS from minus 3 to 0 in steps of 0.5. But here there is no relationship between which is the inner loop and which is the outer loop. So this one has to point to the inner loop. So go to simulation and put here DC1. So it is just telling you that DC1 is the inner loop, and say okay. Okay, it will show up here. So now we are ready for DC simulations. And if I go to simulate and go to simulation characteristics, it says DC CHAR is the same name as the name of the design. So the data set is called this, and the data display window is also called this, right? So that's all fine. I'm just going to save all and hit simulate. Okay, once simulation is done, I can put in a rectangular plot, and I can plot IDS. So these are my curves for different values of VGS. So if you want, you can place here what you call label. So this is for 0, and this is for minus something. So I think the cutoff is minus 1.5. So basically if you go below that, it really is not going to plot anything. So what I'll do is I'll go here and go to sweep VGS, and I will go from minus 2 to, let's say, 2. How's that? Or rather 0 is okay, but I'll add more points. Okay, I can put here 2, 5. So there are 9 curves here. So now I can hit simulate again. So you see the 9 curves here. Now I can also increase this further. So I can go here and I can have a step as 1, 2, 5. So now there are 17 curves. Hit simulate. So these are the 17 curves. So this basically is your output characteristics. So you can insert the text here and say that this is your output characteristics. Okay, now I can change the order of the loops. I can do the GS as the inner loop, VGS as the inner loop, and VDS as the outer loop, and then I can save that result in a different window. So let's do that. Different data set. So I can go to simulation settings, and I would say that this is going to be DC Char 2 and say apply. And then here I can do a VDS sweep, VDS, and I will go from 3 to 5 volts. That's what a battery does, right? 3 to 5 volts. And here I have got 9 of these. So this is your outer loop, and I can do the inner loop inside the DC controller as VGS. So I have swapped the two variables. So this is there, and then I can go from 0 to, let's say, 5 volts or 7 volts. That's okay, and I have more number of points here, and say okay. So now what's going to happen is the inner loop is VGS, the outer loop is VDS, and if I hit simulate, it's going to pop a window. So here you see that the default data set is DC CHAR, where this display is coming from. So if I change this, then this would change, which I don't want to do. So I would say no, and then here I would plot, go to a different data set, which is DCR characteristic 2, and I want to plot IDS. Okay. Okay, so the range of VGS is a depletion mode device, so this range is not right. So I'm going to go from -3 volts to, let's say, +2 volts, or let's say even 1 volt. That's okay, and hit OK. So this is a depletion mode device. Okay, so here you see that the cutoff is around 1.3 -1.3, right? So this is the, I can put a text here, this is the transfer characteristics. Okay, so this is transfer characteristics. So what would output characteristics give me? The slope of these curves will give me the early voltage or the output resistance, while the slope of this curve will give me the transconductance. The non-zero value here would give me the VT, or the threshold voltage, right? This is the information from the transfer characteristics, and here what you see here, that effect will be the, well, I can't say short channel effects, but then they will be like mobility degradation here. So there is a mobility degradation here which you see. Okay, so this is the DC characteristics which I have plotted, correct? Okay, so I can close this, and I can also close this. Okay, so this was DC simulation, right? Now I want to do S parameter simulation on the same circuit. So if I want to do that, I can go and save this as. So before that, let me go back to my presentation, and this is what we have done, right? And we plotted this, right? Now we are going to do S parameter simulation here. Oh, or a small signal. Small signal for active devices. Passive devices do not usually change their behavior with the input power, right? This is because the DC biasing conditions don't change with the input power level, while the active devices, their biasing conditions change as you hit it with power. Okay. Now exception to this are the passives which are on non-linear substrates, right, or non-linear mediums, right? Example, you have got power limiters or using gas discharge tube. So basically these are your what you call isolators or insulators, right? These are used between the transmit and receive section, so their response changes with the input power, right? So these are non-linear in nature. Apart from that, the input power is not going to change the passive behavior, but with the actives it's not like that. So now these actives are diodes, bipolar junction transistor or BJTs, and their cousins HBTs, then field effect transistors like MOSFETs and their cousins PHAMs and stuff like that, right? So they behave differently with variation in input power level because this changes their DC supply. Okay, so you give in a signal. So what is a small signal for a FET is if your input signal amplitude is less than twice of V overdrive, right? So for more details on V overdrive, V overdrive depends on the size for a given current, right? So you can refer to analog circuit design series or playlist which I have. So to understand what is a small signal. So a small signal means that the amplitude is less than twice the V overdrive of the device. Okay, this is for the FETs. For BJTs, this is going to be VT, that is KT over Q, where K is the Boltzmann constant, T is the temperature in Kelvin, and Q is the charge on an electron. So this at room temperature is around 25 millivolts. So that will be considered small signal for BJT. So you can take their DC characteristics and you make a copy of it and change the cell name to another name, right? And then you can, once you have saved that, you can change the the DC controller with the S parameter controller, right? And then you can look at a single point, or you can do a linear simulation across frequency. So let's say I want to do this at 7 gigahertz, and here I can display start, stop, step. Instead of that, I will just display the frequency. Okay, and say okay. So simulation controller is changed. Instead of DC, I'm using S parameter. Okay, so we are not going to go into much into the details of stability, but I want to tell you that small signal stability can be, is usually represented using what is called source and load stability circles. Okay, so what are these circles? If you put a power into a port and you get more power out of the port, so basically it is more than what you put in, that means that circuit must be a source of power, right? So that means it is oscillating, right? It has its own source of power. So if your reflected power is more than the incident power, right, then there is a issue. Now the ratio of the reflected power to the incident power is called reflection coefficient, right? Okay, and so all the points on the Smith chart, which are basically different impedances, which result in a reflection coefficient of 1, which means that the amount of power you put in, the entire power is reflected back. So that will be a reflection coefficient of 1. So all the terminations for that port, all the impedances for that port in which it is terminated, if they cause the gamma in to be 1, that means that entire power is reflected back. So this will show up as a circle. So if the input port is under question, then it will be called source stability circles. If the output port is in question, that is called load stability circle, right? So now you can plot these circles, and then you want to find out the region inside the circle is stable or outside the circle is stable, and for that the test point is the center of the Smith chart. So if the center of the Smith chart lies inside the circle and the magnitude of that S parameter is less than, or reflection parameter is less than 1, that means the region inside is stable. Now if that test point, which is the center of the circle, lies outside and its magnitude is less than 1, then outside of the circuit is stable. Now the other set of condition is if it is inside the circle but then the magnitude is greater than 1, then all the region inside the circle is unstable and outside is stable. And similarly, if the test point is outside the circle and its magnitude is greater than 1, that means everything outside the circle is unstable and inside the circle is stable. Now if the Smith chart is completely enclosed by the circle, right, and the test point, which is the center of the Smith chart, and has a S11 which is less than 1, then the entire Smith chart is stable. The other case is if the circle is totally outside the Smith chart and the center of the Smith chart or the magnitude of S11 or S22 is less than 1, then also the entire Smith chart is stable. So this is called absolute stability condition. Okay, so if these circles are either completely enclosing the Smith chart or completely excluding the Smith chart, then you might have absolute stability. But if they cut the Smith chart into a region, okay, then that is basically not absolutely stable. That's a partially stable condition. So let's try to understand that. So we have S11 and S22 and they are less than 1 in magnitude, so the center of the Smith chart represents that. And you can see both the circles, load and source stability circles, are completely enclosing the Smith chart. So that means the entire Smith chart is stable. Now another condition is they are totally outside, but that the center of the Smith chart, which is magnitude of S11 and S22, is less than 1, then also the entire Smith chart is stable. Okay, so what is going to happen is I'm going to have a ready-made component which is available under S parameter simulation palette, which is called source stability circle and load stability circle, and I'm going to place them. So mind you, this we are doing at a single frequency, so these circles would be plotted at single frequency, which is 7 gigahertz here. So once you place that and you hit simulation and then you draw the Smith chart, you can plot these, okay, and go to plotting options. You do not want to auto scale it, so you fix it to 1 or 1.1, and now you see that the circles are not either completely outside or completely enclosing. So that means that they are cutting the Smith chart into 2 regions. Now we have to find out which region is stable. Now we know S11 and S22 magnitude is less than 1 because these 2 points are inside the Smith chart, right? So that means that the center of the Smith chart is in the stable region. So all the shaded portion is stable for the source and then the load, right? So that's there. If it is not stable, then you have to stabilize it first. Now absolute stability is overkill. So if you do it matching, for example, if you do a combination of low pass high pass matching, right, on input and output side of a transistor, and you just restrict your band to go through, so it will be a band pass kind of a match, right, then the low frequency and high frequency stabilities would to some extent be improved, right? But despite that, if you have instabilities, then you need certain stabilization, right? So one way to stabilize at high frequency is something known as source degeneration. So you can put in a inductor here, right? Other way is to put the series L and C across the drain and gate. So that is called lead compensation, right? So this will introduce a zero between the dominant pole and the second pole. And if you want to read more about the Bode plot of a transistor, I'm referring you to analog circuit design series, right? So follow that, you will know what that lead compensation is. Okay, so you can place a resistor here, a capacitor here for stabilization, or you can place an inductor here for stabilization. Now this inductor would be replaced by a trace of line, which may be a meandered line and things like that in the layout. Okay, then you can resimulate the circuit. Now you see that both the circles are completely outside. I'm zooming in where they're touching, but they are still outside, right? And then this device is absolutely stable. Now I can do the matching anywhere, right? So I can do a simultaneous conjugate match for input and output. That means I'll move S11 and S2 to the center. Okay. So I'm going to display admittance chart also, and then I'm going to do this kind of tuning, and I would have a stage which is going to be stable. So don't be overwhelmed by what this is. Okay, all this is that I have got certain matching on the input and output side, and then the ideal chokes are replaced by inductors, right? So I'm going to place this as is, because I don't want to teach you matching in this, right, session. So this is your input match, that's your output match, and these points are shorted by these bypass caps, and these are the bond wires, right? So you can, once you have done this, you can hit the simulation. Now here you can simulate over a range. So I'm going from 100 megahertz to 10 gigahertz in steps of 100 megahertz. So not just one stability, you have many stability cycles, right? Same thing I can also put here enable the noise. So basically in the band of interest, so this I set the frequency to my band of interest, which is 5.5 to 8.5, let's say, and then go to noise, and then I am going to say enable noise, and then I'm going to put here options. Okay, so noise figure measurements in IEEE standards are at 16.85 degrees C. So I have to set the simulation temperature to be 16.85, so which I do using option component. So that's what I'm doing here. Okay, then simulate the circuit and add a rectangular display to add this gain and return losses. So return loss better than 10, and then I can plot noise figure and noise figure min. So noise figure is better than 1.4 dB. So if you want more details onto this, you have I'm directing you to microwave and millimeter wave circuit design series in my YouTube channel. Okay, so once you are done with this, you have done matching of a transistor to get a certain gain and a noise figure. So that's a LNA, right? Okay, so we are going to do that. So I'm going to put this on the side, and I'm going to focus on this one. Okay, so here we are as schematic. So I can just say right click and say copy cell, and I call this as SPCHAR, right? And I can choose a different folder for that, because I'm not doing any DC characteristics now. But the thing is, I should have a folder declared before, so I can just say OK for now, and I can make a new folder here. So I call this as SParam, CHAR. So S parameter characteristics folder, and here I'm going to drag this to this folder, and I have it over here available. So first thing I'm going to do is I have to choose a bias point, right? So I will refer to my display window for DC simulation. So if I go to the main window, this is my DC characteristics. So let's say I bias it at with 4 volts with a current of, let's say, 50 milliamps. So this would be that. So if I put a marker here, file new, and this would be 4 volts, this will be around 50 milliamps current, correct? So this is biased at minus 7.5. Let's see what this is biased at. Refer to my slide. Okay, so where's that variable? minus 0.9. Okay, let's see what is at minus 0.9. Okay, so go back to DC simulation. So this is 0.7. So I'm biasing it further low. So this is at minus 8.875. This is minus 1. So let's bias it over here. Now the quiescent current is going to be 34 milliamps. And VGS is equal to minus 0.875, right? From a 4-volt supply. So let's set that 0.875. So I have biased that from a 4-volt supply, correct? And I am going to delete this. I'm going to delete this, and I'm going to add simulation S parameters. Simulation S parameters. And here I'm going to do a single point, which is going to be single, and I'm going to look at 7 gigahertz here, correct? So here I want to display something. I can go to display option. Here instead of start stop step, I just display the frequency, FREQ frequency. So I'm simulating at 7 gigahertz, right? And here I have no stabilization here or here. I will look at the source and load stability circles. So there is a load stability circle here, and then there is a source stability circle here, right? So I'm all set for simulation. I'll hit simulate. Okay, so one thing you can do is you can do simulate, annotate DC, or you can annotate voltage and currents here. So if I annotate current here, so it's drawing 34 milliamps of current, right? So that's what it shows, right? 34 milliamps of current it's drawing. Okay, so I can also clear annotation. You can also annotate the voltages, right? So everything looks okay. So over here, I want to look at 2 points, which is S11 and S22. So they are over here. One is over here, and the other one is over here. Okay, so it is not matched. But I also want to look at the magnitude of S11 and S22. So S11 add, so I can say magnitude, MAG. Okay, so it displays the magnitude is less than 1, right? So that's what we were talking about. So that basically is the center of the Smith chart. And then let's look at S22. Here also I'm going to plot the magnitude. Right. So both the magnitudes are less than 1. Right. Now I'm going to put the stability circle. So I'm going to put the load stability circle. So here I don't have I have the auto scale. So now the Smith chart is much reduced. I don't want to do that. I'm going to go to plot option, and I'm going to say that it is 1. So that's your overlap. So here I'm going to put green color. So this is related to the output port. So this is your load stability circle, and then I will go to source stability circle. Source stability, where is it? Why don't I have a source stability circle? Cancel. Okay, stability region, it says stability circle. Okay, I'll simulate again. Now this other buttons, actually you don't have to worry about them for now. Okay, so I'm going to plot here source stability circle, and that's that. So I'm going to give this a different color, let's say brown. Okay, so now the region of the Smith chart, which is stable, right? That region, of course, I cannot draw smoothly, but I'll try. So all this region which I'm putting as a boundary, so just bear with me. There's no smooth way of drawing this. So I'm doing a rough drawing. Okay, all that region which I just marked, I'm going to fill it. Okay, so I'm going to use a fill pattern, and I'm going to say, okay, so entire this region which I have plotted here is stable, okay, because the test point is in the stable region, right? So what I want to do is move these circles out, not only out for my frequency but also for all other frequencies. So I know that transistor is absolutely stable, but this is an overkill. Okay, so let's put in here a certain inductance. So basically you might have to split this inductance into two. So I might go here to linear component, to lump components, ideal component, and let me rotate this out. Okay, so let's put two inductors, and in layout I'll show you why two inductors. Okay, if you refer to my series on microwave and millimeter wave circuit design, you'll be clear what these two inductors are. Okay, and let's set their values to be 200 pico. 200 pico. Okay, so this is a high frequency stability. Okay, and I'll just tell you how to handle low frequency stability. Okay, so this is your negative feedback or source degeneration. Then I'm going to use a resistor here, and I might be done with only one, but let's say if I put both of them, and then it really depends on the lead compensation. Basically I'm just doing by rule of thumb, but you can go into details of what is lead compensation and then do it. So here let's refer to my schematic. Okay, so these values are okay, so let's look at this side. Okay, so I don't have, so I have to replace the other ones, but it's okay. So the resistor value is 800 ohms and 0.25 picofarad. So this is 800 ohms. The smaller the resistor, higher is the feedback. 0.25. So this is for adjusting your 0. Okay, so we are done with this, and we will just simulate this. So you see that it has almost moved out, correct? So what you can do is you can increase this further to, let's say, 230 and 230 and hit simulate. So they are moving out. You can zoom in, right? You can reduce this to 700 maybe, or 750, and you simulate again. Okay, so this brown one is still not outside, right? Okay, so let's make this 260. So the effective is going to be parallel combination, which is 130. Okay, so now they are completely outside. Now, is this the situation for all of the frequencies? I'm not sure, right? So in that case, I can do it over a frequency. Let's say I want to do it linear, and I want to look at 100 megahertz to 10 gigahertz, let's say, in steps of 100 megahertz. Right, so I'm taking 100 points here. So I'll have 100 of those circles for each input and output. Okay, so it seems like I can remove this, delete. Seems like you have some stability issues over here because these have got inside the Smith chart, right? So in that case, I can increase this further to, let's say, 280, and this to 280, and hit simulate. So I haven't moved much. Okay, one of the major reasons can be these DC feeds, which are ideal. So here I have to put here inductors. So I'll go to nonlinear demo kit and look at this inductor. Rotate this, place it over here, place it over here. So right now this is 2.5 turns, and this is the inductor value. So only way to change the inductance is through the turns. Or what about the size? It doesn't let you change the size of the inductor. Okay, or we will live with this, doesn't matter. And I will just copy these capacitors as bypass gaps. So I will copy these like this. I'll copy them over here, and I'll copy them over the other side. Correct? So don't worry about this overlapping. Okay, so now it looks okay. I'll move this text to the inside. Okay, and here I'm supposed to put this capacitors through a via. So this is there, this is there, and then I should put a via. So this is a fat via, this is a back via. So this is one via, and this one I can rotate as another via. And I'm just gonna connect this over here, and this capacitor text I'll move. Okay, so here I'll connect this one. Okay, so the loss in this line also basically to do with the small. So this frequencies, if you check, these frequencies are going to be low frequencies, lower than our band, which are unstable. Right, you see 800 megahertz, 400 megahertz. So we have done a high frequency stabilization, but what about the low frequency? That will happen through the loss in here and loss in here. If it simulate, okay, it's even worse. Okay, what it says, okay, the board via here, it is not characterized to those values, those high frequencies. So that's the problem. And even the back via here. Okay, so let's see what we did in our PPT. We are just using ideal components. Okay, so this is not characterized, so this is the demo kit. So if demo kit doesn't have it, then don't have it. So that's there. I'm going to hit simulate. Okay, So capacitors C3, C8, C9, C7 are shorted out. Which capacitors are shorted out and why? C3, C8, C9. Okay. These are referring to these capacitors. Okay, I don't see a short other than if you have a small RF short here. Okay, I can put a bond wire here, right? Roughly the bond wires are few nanohenries. But the problem remains here is what do you do with the low frequency stabilization? So here, let's say if I put a 5 ohm resistor, let's say. Okay, so here I'm going to put a 5 ohm resistor or a 10 ohm resistor. So as the FAT doesn't draw any current, you can put a high resistance here. Bear with me. This is clumsy. Okay, so this resistance I can put as 10 ohm or 5 ohm, let's say. And this is going to affect your it cannot be less than 25 ohm. Is there any other resistor model here? No. So let's put it 25 ohm. Doesn't matter. What? Width 62 ohms. So let's make this width of 40. And let's see if it accepts 25. It accepts 31. Okay, let it be 31. If I hit simulate, I just wanted to show you how to fix the low frequency stability. So now you can see this was all low frequency instability. So there is no point in increasing this because it is not because of that. This is for high frequency stabilization, right? And your voltages will hardly change because the FAT doesn't draw any current, right? So you can put as high a resistor as you like here. Okay, so you see everything is outside. Clear? Okay. So now we have a stage which is almost matched, right? So I may not do any other matching. Okay, what I can do is I can adjust this inductor value, right? So these inductor values I can adjust, and let's see in my band of interest what's happening. Okay, so you understood that what is a high frequency stabilization and what is a low frequency stabilization. So both are different. So you have to check where your transistor is unstable. Right. So don't worry about these straight lines because these straight lines are because usually the circles have to have their endpoints. Otherwise, ADS will draw a line between the two endpoints. So that's not a part of the circle. Okay. So here my region of interest, I want to tune for that. Correct. So everything is simplified for you in the demo kit, but the real PDKs, they are more erratic in behavior. Okay, so here I am going to just change my frequency. Okay, I am going to go from what frequency band are we looking at? Look at the PPT. So I am going to look at 5.5 to 8.5. Let's look at that. So I'm going to go from 5.5 gigahertz. Sorry. To 8.5 gigahertz. Okay, and hit simulate. Okay, so this is my matching. It just shows that if I want to move these points up, Okay, so if I was here, shunt inductor was taking me that way, and then a capacitor was taking me that way. Oh, sorry, a shunt series inductor would take me that way, but then there is a capacitor here. So if I increase the capacitance value, these will go up. Okay, so there is no way I can increase this capacitance, right? So if I lower this inductance, so let's say this is 2.5. So if I simulate that, okay, and lower this inductance, so I have to increase this inductance, 7.5. This is input side, right? Let's see it again. The red one is input side, so I have to increase this to bring it closer. Hit simulate. Okay, the capacitance has to be increased. The capacitance has to be further increased. On the input side, if I put 3 capacitors, okay, so this demo kit is not something, so not working. Okay, so now, okay, I can simply bring in, sorry, I can simply bring in certain inductance here. Really doesn't matter. Okay, I can bring in some inductance here. So let's go to inductor and place a small inductance in here. And I have only way to tune this is by changing the number of turns. So let's say 1.5. Okay, so this is 0.56 nanohenry. Hit the simulate button. Okay, so this has moved way up now. Okay, so I need a smaller inductance than that, and this is going to be crazy because it will not allow me 1. I'm sure about this. Let's see if it allows me 1. Okay, it did. Then I say okay. So it's over here. That means that this inductor has to go up. Another thing is what is happening to this guy. Okay. Okay. Simulate, annotate DC. Let's look at the currents. So that's 34 milliamps. Let's see if this will help me tune this slightly. And hit simulate. Okay. Okay. What? This one was 1.5, right? Or rather 2.5, right? Why did it change? It's not supposed to change, right? Okay. 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 So now they are coming closer. Okay, so this inductor value can be increased to 1.5. So okay, simulate this. Okay, so that has come closer. And this one, I can change the capacitance. I can further lower this down to 1.1. 7.5. Okay, so they have come closer. Okay, so now I will be able to plot so now you can see it is stable, right? And I'll be able to plot S21. So that's my gain. The gain is between 12.5 and 11, right? So 1.5 dB variation in gain. And then I can put here S11 to correspond to a return loss. So they are better than 10 here. So I'll make this one as green. And this one as blue. So that's what that is. Right. Now, if I was to do a noise analysis, so first of all, I'll go to the S parameter simulation and I will go to options. So where do I see options? Options. And here I'm going to set the simulation temperature, device temperature to be 16.85. 16.85, and that's kind of weird, but all the specifications are at that. Okay, so you're done with that and you hit simulate. Okay, so here I want to look at noise figure, so go to somewhere it says noise figure. Okay, it doesn't say here, so you have to go to simulation and here go to noise and calculate noise and say okay. And when you hit simulate, you can plot here the noise figure. You can go here and NF2 and NF min. Okay, so right now it is 2 point something and NF min is 2.4. Now it's bad because it depends really on this one, source degeneration. So if I was to do this 8 and this 8, I might have to do rematching. It should come down, right? 2.3, 2.8. Okay, let's do this. Let's change the bias current. So I can set this bias current to be something little higher. Okay, not budging. So what may be the source of this? Is it the matching? No. So I'm not going to struggle with this because this is not a session for designing the LNA. So I'm just going to accept it as is. So what I have done is I've shown you this, and I can also put the noise figure circles. So let's say noise factor, gain circles, load source noise. So these are noise factor circles. And if I hit simulate, and I can plot here NF and circles. So there will be many circles. So you are best matched for noise somewhere over here, right? It's passing through that point, so it really doesn't matter. Okay, so this will be your noise circles, and then you can do a optimization between, or rather trade-off between. Let's say if I put the gain circles here, right? So why there are two gain circles? Okay, so I can put the gain circles here. Okay, so they are centered on the center of the Smith chart. So usually the transistors don't behave like this, but this is a demo kit. Okay, so I've shown you a lot of things related to S parameter and how to do the S parameter simulation and how to do the matching. And I'm going to stop here in this chapter 2.